As an introduction to amplifier selection, I'd like to talk for a few minutes about how amplifiers behave under different load conditions. In the graphic shown, the amplifier is the source and the loudspeaker is the load. The loudspeaker is treated as a simple resistor. Here's what the equivalent circuit looks like. If additional loads are added, they are paralleled, or daisy-chained, with the first one. This reduces the impedance seen by the source. If too many loads are paralleled, the impedance becomes too low, and the amplifier can't source enough current. The amplifier is overloaded, and its output voltage drops. The current limiting and voltage drop are usually accompanied by an increase in distortion. The amplifier's performance is optimal when it's operating as a constant voltage source. This fact should influence our philosophy with regard to amplifier loading. In a perfect world, an amplifier would behave as an ideal voltage source. A voltage source is one whose output voltage is independent of the load impedance. The more you load it down, the more current that flows. And more current flow means that more power is delivered to the load. The plot shows the behavior of this ideal voltage source. Since the voltage remains constant as the impedance drops, the more you load it, the more power you get. If real-world amplifiers worked that way, we might be tempted to load them down to get more power. Real-world amplifiers will run out of current as the load impedance is reduced. The current limiting is accompanied by a voltage drop. Note that this amplifier has the highest output power at 2 ohms, but the highest output voltage at 8 ohms. The plot shows this behavior. The amplifier is fully loaded at the impedance which causes the output voltage to drop. Loading it further reduces the output level, increases the distortion, may engage a protection circuit, or may even damage the amplifier. It's the 8 ohm load that's optimal for this amplifier, at least for a sine wave signal. Broadband program material has a higher crest factor, and this amplifier could probably drive 4 ohms without current limiting and voltage drop. The takeaway is that amplifiers have a minimum impedance that they can safely drive. Lower impedances should be avoided. An amplifier's behavior at overload varies by design. But in all cases, audio performance suffers. Hopefully the amplifier has a protection circuit that at least keeps it from being damaged. A protection mechanism that's gaining popularity is the constant power design. This amplifier, when overloaded, simply turns itself down. It can drive any impedance, all the way down to less than 1 ohm. Here's a plot of this amplifier's behavior. Note that it is still optimal to keep the load impedance from getting too low, but at least if it does, the amplifier won't be damaged. To summarize, an amplifier is fully loaded at the impedance at which its output voltage starts to drop. To complicate matters, this minimum impedance is dependent on the crest factor of the program material. For example, a low crest factor signal, like a sine wave, will have a higher minimum impedance than a high crest factor signal, like pink noise. I'll address this further in the next lesson on amplifier specifications.